Hello to my AP Stats students. Today we are talking Unit 5 Lesson 3, which is all about sampling distributions of sample means. The last time we talked about proportions, now we talk about means. This is the final sampling distribution that we are going to really focus on in this course, so let's get right to it. We'll start off with our EQ that will sound very familiar from our last lesson. How can we describe the shape, center, and spread of its sampling distribution, but now sample means? Now, let's go ahead and take a look at an example of a situation in which we might be interested in looking at sample averages. So below is the population distribution of household incomes in a typical U.S. city, and we've identified below the mean income with this arrow. So this is mu, right down here. This is the true population mean. And that true population mean is somewhere like around $70,000 for the mean income. But is that where most of our individuals are? And the answer is pretty clearly no. Most of our individuals have something that's less than that average, but it's skewed high because we got like these CEOs, these influencers, and these all-star athletes and things like that in a U.S. city that are going to be making a lot more money, and that's skewing that average high. So the question now is, if you were interested in seeing what is the mean income, well, what happens if you take a random sample? Because you know that a random sample is supposed to be representative of the population. So if you randomly selected one sample from this city, do you think its sample mean X bar would reliably estimate the average income? Well, what are we most likely to see? We're most likely to see these guys right here. And that would tell me I'm most likely to underestimate the mean from just one sample, since I'm not very likely to get these extremely high outcomes that are over here. If I do get one of those high ones, then I'll probably get pretty close to the mean, but that might not be super likely. So what do? Well, as statisticians, we should know that, hey, if we want to have something that's more reliable, take more individuals in your sample, or even better, take lots and lots of samples. So what if we sampled many houses, and not just many houses, but we do this many, many times? We create a sampling distribution. And so below is the sampling distribution of the sample mean X bar. And we can see that the center of this sampling distribution is indeed the same as the population distribution. So mu sub X bar is the same thing as the population mean. So now you ask yourself, would the average of all sample means, mu sub X bar, be more or less reliable than just one sample mean? And we should see that it's going to be much more reliable. Not only does the average actually line up, what we would most likely expect to see, does it line up with the population mean, but it's a lot less variable, okay? Even my sample means that are extreme, the ones that are way over here at the very end, they are much, much closer to the true mean. And thus, we can say that mu sub X bar, the average sample mean, will be the same as the population mean. And that tells us it's an unbiased estimator. Now, like all proportions that we talked about in the last unit from section Unit 5, Lesson 2, the sampling distributions of a sample mean are also unbiased and will often follow a normal distribution. So, if we can identify the shape as being normal, we can identify reliably the center and spread as well of the sampling distribution of X bar, then that means we can do the same thing we did in Lesson 2. Work with norm CDF style probabilities to find if one sample mean is typical or strange. Let's see how we can identify those shapes, center, and spread. So what are the characteristics of the sampling distribution of the sample mean? Well, let's first talk about the shape. We know that the shape, we want it to be approximately normal. And we think back to what we did with proportions in the last unit. And we said that, hey, we know that the shape is going to be normal if that large counts condition is satisfied. Well, the large counts condition was saying n times p must be greater than or equal to 10, and n times 1 minus p must be greater than or equal to 10. The successes and failures must be greater than or equal to 10. But now, look at what we're talking about. We're not talking about proportions anymore. We're talking about means. There are no right or wrong. There is no success or failure anymore. Okay, now it's much more fluid. This is quantitative data, and we're talking about individual values that can take any number of values. So it's not just success or fail, but now we have to find something else. And there's actually 3 ways that we can see that our sampling distribution of the sample mean will be approximately normal. It's going to be approximately normal if the population is known to be normally distributed, then your sampling distribution is also going to be approximately normal. So that's interesting, right? As long as we can see that our population is normal, boom, hey, our condition is satisfied. We know our sampling distribution is going to be approximately normal too. However, if our population is not normally distributed, or we don't know if it's normally distributed, then as long as we take a sufficiently large sample, then we should be good to go. And that seems to make sense because remember, we had to check the LCC before. And if we have a sufficiently large sample, then the sampling distribution of X bar is also going to be approximately normal. Well, how large is sufficiently large? This is where a lot of statisticians have done the hard work for you. And they came up with the central limit theorem. And the central limit theorem says if you have a sample size that is more than 30 or at least 30, then your sampling distribution is going to be approximately normal. Next, we can also say something about the center. Now, remember from when we were looking at proportions that the mu sub p hat is equal to p. The average sample proportion should be equal to the population proportion. It's what told us we had unbiased estimators, that the proportion will usually, or on average, adequately estimate the sample proportion, or the population proportion. And the same is going to be true with means. We found that sample means are also unbiased estimators, which means that mu sub x bar will equal the true average. The average sample mean will be the same as the population mean. No condition to check, it just is what it is. That's one of the benefits of working with sample means. Next, we talk about spread. So spread, remember that we had to check the 10% condition. Our sample must have been less than 10% of our population in order for us to be able to reliably calculate the standard deviation, the sampling distribution. And the same is going to be true when we start talking about means. The spread of the sampling distribution of the sample means behaves similarly to proportions, which means it must follow that 10% condition in order to calculate a valid standard deviation. Thus, if your 10% condition is satisfied, if your sample is less than 10% of your population, then we can calculate the standard deviation. And this is a much simpler formula. It's the population standard deviation divided by the square root of n. Sigma over square root n. That's your formula to be able to calculate the standard deviation for sample means. Now, once you know a sampling distribution of X bar is approximately normal, then you can use norm CDF calculations. And that's going to be the easiest way to go. However, sometimes on multiple choice questions, you are asked to start to look at the z-score or calculate a z-score or identify what's the correct formula to find the probability. And so remember that z-scores is x minus mu over sigma, where we have observation x minus the true average, and divide that by the standard deviation. Well, our observation in this case is always going to be the sample, what we get from one individual sample. So x becomes x bar. Mu, what's supposed to be true for the entire population, well, we know that that's going to be the same thing as the mu sub x bar. It's what's supposed to be true for the average sample. And then our standard deviation now is based off of not sigma anymore, not the population standard deviation, but it's based off of the sampling distribution's standard deviation. Thus, we look at sigma sub x bar. So all of that gives us this formula when we want to calculate a z-score, x bar minus mu over sigma over square root of n. And that looks gross, but I promise you, as you get into practice with this, it's going to get easier and easier and easier. Now, make sure to remember to draw any pictures of any normal curves that you are making and label all of your inputs when you're doing your norm CDF calculations. This z-score formula is not needed for an FRQ generally, but you are more likely to see that on a multiple choice question. Now, before we head out, let's go ahead and wrap everything up with a nice summary that answers that essential question of how can we describe the shape, center, and spread of the sampling distribution of sample means? Well, we should know by now that the shape is going to be normal. We have two ways of knowing that the shape is going to be normal. If your population is normal, or that CLT is satisfied. Remember that CLT is saying that your sample is sufficiently large. Your sample is at least 30. The center, we know we can describe that very simply because it's an unbiased estimator, which means the mean of its sampling distribution is equal to the population mean. And then finally, our spread. So long as the 10% condition is met, we can calculate the standard deviation with this formula where sigma sub x bar is going to be equal to the standard deviation of the entire population divided by the square root of n, your sample size. That does it. We know how to describe our shape, center, and spread of a sampling distribution of sample means, and we know the conditions that we need to check. The great news is these conditions are even easier than the ones that you had to deal with in the last lesson. So let's get to it. Practice, practice, practice. I will see you next time. Thanks for watching.